comparison test for convergence. There's two of them. So sometimes we may encounter series that deviates ever so slightly from our normal looking series. For example, I have the summation 1 over 2 to the n is geometric, but n over 2 to the n is not. 1 over n to the third is a p-series, but 5n over n cubed plus 8 is not, and so forth. This right here features an a sub n expression that is can easily be interpreted, but this one right here is a little bit harder to do. Okay, so what we need is a new test for this, and so then we come up with a comparison test. So the first one we're going to look at is the direct comparison test. Okay, if we have two sequences, a sub n and b sub n, a sub n is less than b, but they're always greater than 0 for all n, then if b converges, then the a sum series converges as well. Because these are all term by term smaller than this one, so if this one converges, means it gets closer to a number the farther out we go, then it forces this one to follow the same path and get closer to that same number also. Okay, that's the idea we're doing. This is not very popular on the AP exam, just a little side note there. The next one would be more appropriate, but it is here. Okay, it does require a little bit of effort to set up, and so we're going to look at that and see how to go about doing that. The nth term expression of the given series can play the role of either a sub n or b sub n. It is necessary that we can make a term-by-term comparison for a sub n and b sub n. We need to know which is smaller and which is bigger to make this work. We need to know which one is where. Okay? So, let's look at our first example, and I'll show you how we go about doing this. So the first one is going to be this one right here. It's the summation n equals 1 to infinity of 1 over 2 plus 3 to the n. So, excuse me. Let me draw a little line here, and we'll do the other one over there in just a moment. So we want to start by selecting a series that resembles our series, okay, our given series. And how do I go about doing that? Well, usually what you can do is just eliminate anything that's not, that's not nice. So the plus 2 here, we can get rid of that. So we can use that as our series to compare with. So let's do that. So let's look at the summation n equals 1 to infinity of 1 over 3 to the n. Something simple we're going to compare with this. We want to choose something that we can determine the convergence or divergence of. So we want to make it kind of as simple as possible. So by looking at this, we can see that this is a geometric, okay, this is a geometric series right here, where r, okay, is equal to 1/3, which is less than 1. So we know this is convergent by the geometric series. Okay? Now we need to compare term by term. We also know that this expression, so we also know that 1 over 2 plus 3 to the n will always be less than or equal to 1 over 3 to the n. This bottom number will always be bigger than this one, so this fraction will always be smaller than this one. And this is true for n greater than or equal to 1, so we have to do that step too. Okay? So we know our nth term is smaller than this nth term. We know that this series here converges. Okay? So because of all that, because n equals 1 to infinity of 1 over 3 to the n converges, then I know that this one right here of 1 over 2 plus 3 to the n also converges. And that's by direct comparison test. Okay, so let's recap again real quick. I got to choose my own function. I want to choose one that is similar to this one right here, that I know if it can converge or not. I need to find something appropriate so that I can compare it to this one and do it term by term. So I have to know that this one is either bigger or smaller than the one I have chosen. Okay? It's important to pick it in a way that the behavior of this one tells me the behavior of mine. Okay? So if I had this right here was convergent, and then I show that this term is bigger than ours, then I can't say by direct comparison that ours is going to converge. It has to be less than. The bigger one is convergent, so I need mine to be smaller than that one so that mine has to converge also. Okay? Let's take a look at another example. This one over here. And again, we start by selecting a series that I can compare mine to. So since this one is 1 over 5 plus the square root of n, I'm probably just going to eliminate the 5 and use mine. I'm going to choose a simpler version of that, 1 over the square root of n. And then this I'll write as a exponent. And this will be 1 over n to the 1/2. So this right here is a p-series, okay? And so the p-series, and I can see that our p is equal to 1/2, which is less than 1, which means this series is going to diverge. Okay? Now we're going to compare to ours. Okay? So I know that 1 over 5 plus the square root of n is always going to be less than or equal to 1 over the square root of n for n greater than or equal to 1. So what does this tell me? Well, this is what I was talking about. This one right here diverges, and this is smaller than that. So because of that, I can't tell what happens with this thing. Okay, it doesn't force this being divergent, doesn't force this to be divergent. Okay, so that's a problem we have with that. So this right here is, we can't do this comparison. This comparison did not work for us. Okay, so let me go ahead and show you the little side notes I had for this one, so you can kind of write it down too. That'll explain exactly what I just said in written form, and you can pause right now and copy that down if you want to. But it's what I just said. This right here diverges, and this is less than that. This is not a good series to compare with. It doesn't force this to follow it. So this one we cannot use the direct comparison with this chosen series. We can try and find a different series that might work for us, but this one does not work. Okay? So let's look at the next part of this. And you can see that that's where we're going to be heading here. Kind of discussing what we just discovered up here. Let's try again with a different comparison function. This time let's try 1 over n. Okay, the series 1 over n. We know that this is a divergent harmonic series. This is the harmonic series, so we know it's divergent. We can establish the relationship because we know that this right here, this will always be less than that for n greater than or equal to 8. So below 8 it's not, but bigger than 8 it is. And that's fine because we're going out to infinity, so it's okay to go past a certain number. And you can look into this how I know. So if I was at 1, this would be 1, but this over here would be 1/6. See? But at 8, or past 8, and that's not going to be the case, okay? And you can do a test yourself, a little cross multiplication. You can see that when there's an 8 in here, it's going to flip over, and you can see that it doesn't work. All right? Now because the lower series diverges, then that will force the larger series to diverge also. So because this one is a divergent series, does not approach a number, it basically goes to infinity, that forces this one to do the same thing. It forces it to go off to infinity also. So then this diverges by the direct comparison test with this series here as the comparison. The last thing you want to do here that I have as a little note here is be sure that you state this reason why. So this diverges by the direct comparison test. Make sure you state that as part of your answer. Okay? So let's continue on, and here's another couple notes here. When trying to implement the direct comparison test, you must choose a series that looks like our given series. We must also be sure of the chosen series convergent or divergent behavior. It is important that we establish the direct comparison, the correct inequality, this part right here, okay, between our given series and the comparable series expression. So you want to make sure that happens. Okay, you have to establish this, you have to establish the final answer here. You got to show that the direct comparison part of it. All right, our biggest challenges with using the direct comparison test is that it can be difficult to establish a term-by-term comparison between your given series expression and the comparable series expression, that the comparable, the one you chose over here. The limit comparison test makes this easier. So let's take a look at this. I'll move it up here so you can pause and try and write that down if you need to, so that you understand the nature of things. All right, let's look at the limit comparison test. How is it different? Limit comparison test. So if we have a series or a sequence that is greater than 0 and another one that is greater than 0, and the limit as n goes to infinity of this ratio of those items, of those sequences, and that comes to has a limit. Okay, if this L is finite and positive, then the two series either both converge or they both diverge. Okay, you need to know the convergent or divergent behavior of your comparable series. Okay, because they're either going to, so if I know this here converges, this series converges, okay, so let's say this is my original one and this is my comparing one. If I know this diverges and then I get this thing to happen, well then that tells me then, because either they both converge or both diverge, since this converges, so does this, or vice versa. Let's take a look. Here's our little note here for this. Okay. We will not use an alternating series because those two values here have to be greater than 0. Okay, so we're not going to use this with an alternating series. That has its own special little techniques. It does not matter which series expression, the given or the chosen, that we put in the numerator. Okay, that doesn't matter. But be consistent. Okay, I usually put the original series expression in the numerator. But you can do however you can do it the other way around if you want. Okay, but always do the same way. Don't go back and forth, because then it's just going to mess you up. All right, so let's look at some examples of this. Here's our first one. I'm going to draw a little line here in the middle. We're going to look at this one right here. All right, determine the convergence or divergence of this series right here. And so the first thing we want to do is find a series that resembles this. Okay, and so what you want to do is, in your first go, I mean, you can try different things, but the easiest way to do it is just eliminate any adding or subtracting things like this and just get to the main ones here in the front. So if I try, and again, it may not work, I'm going to try this one. And I'm going to dump the +1. This gives me the square root of n over n squared, which I can then change this into a power, or a p series. N equals 3 over 2, because that's a 1/2, and you bring it to the bottom, it becomes -1/2, and that gives me the 3 over 2 exponent in the bottom. So I know this is a p series. Okay, this is a p series. P is equal to 3 over 2, which is greater than 1, so I know this series converges. So I need to know the convergence or divergence of my series. Okay, with that, I can now take the limit as n goes to infinity, and I'm going to put the original one on top, and then r's in the bottom, and then we're going to work this out to simplify it and see what comes out of this. It goes to infinity. Flip the bottom one here, multiply it to the top, and so this is going to go up to the top with that one, so then you're going to add the exponents and all that good stuff. And what you end up with is n squared over n squared plus 1. And as n goes to infinity, this is 1. Okay? And since that is the positive number we were looking for, finite and positive, so then I know what? By the limit comparison test, this series also converges, because the one we compared it to converged. The limit was a number, a positive number. Therefore, since either they both converge or they both diverge, ours converges also. Okay? Let's take a look at this one over here and see if we can work that one out. So now they're getting a little bit more complicated and the looks of these things. So we have to choose something that looks similar to this. So what can I eliminate from here to clean all this kind of stuff up? Again, anything with like little numbers and stuff, we can kind of like eliminate. We don't need to have it. All right? So I can try this one. Let's do n equals 1 to infinity. If I dump that right there, then that n and that n cubed can reduce. Okay? And then the 4 is just 4 times something on the bottom, so I don't think I really need that either. So I can probably compare it to this thing right here. So the question is, what do I know about this? Okay, well, this is an exponential, and this is like a polynomial, and exponentials grow faster than polynomials, so this right here is going to diverge. Okay, so let's do our limit. As n goes to infinity, again, put the original on top. I do. You can put the original on the bottom if you want. Divided by this. And then we want to clean this up. And over here we'll have n times 2 to the n over 4n cubed plus 1 times this thing over here. So we flip it over and get n squared over 2 to the n. And so you'll notice some things here are going to disappear. The 2 to the n's drop out. Okay, these on top gives me n to the third of n cubed over 4n cubed plus 1. Well, we've seen these before. So as n goes to infinity, it's the leading coefficient, so this here is equal to 1/4. So again, we have a number. So by the limit comparison test, because our compared series diverges, ours diverges. So because this one diverges, then this one diverges. Okay, so let's take a look at the final notes over here, and then that's how that works. You'll probably use this one more often than the direct one. So make sure you understand the criteria for this one. You can see it's a lot easier to deal with. You're still doing a comparison, so if you want to, take a pause here, and you can write down some of the little side notes that I have for this problem that we just did. And then also here at the very bottom, some finishing notes that I have here for you. in both the comparison tests, the direct and the limit comparison, we find a series that looks like ours, and we must know if it converges or diverges. Unlike the direct comparison test, the limit comparison test you do not have to establish a term-by-term comparison between them. Okay? So there's no inequality statement. The direct comparison, it's not used often on the AP exam. The limit comparison will most likely be on the AP exam. So you definitely want to make sure you understand the limit one quite well. Okay? So there's the comparison test, and let me know if you have any questions.